Hello, everybody. Thank you very much, John, for this nice introduction. Today's webinar is about an introduction to wet gas flow metering. This is a webinar that we have run in the past, but we received a lot of attention on this topic, and people asking to run it again. So here we are. And I'm pleased that there is a lot of persons enrolling in this webinar. So it means that wet gas flow metering is a topic of interest for a lot of people. This is an introduction. So, of course, in 40, 45 minutes, we will not be able to cover all the aspects of wet gas flow metering. But hopefully it will be a nice overview. We will start with a brief introduction of the National Engineering Laboratory to suit NEL. We will move then to some terminology and the main application of wet gas metering, and later the importance of flow patterns, followed by a focus on differential pressure meters in wet gas flow. Then on some R&D project we are running, and we will end up with a summary and a Q&A session. So let's start. What is the National Engineering Laboratory? Well, it's a laboratory that was established in Kilbride in Scotland in 1947, and it was a UK government research laboratory. In 1995 was privatized, and now it's part of TUSUIT. We conduct a lot of research on behalf of the UK government still, and we hold the national standard for flow measurement and density. So as I was saying, we are part of the UK National Measurement System, and we are the designated institute for flow and density metrology. So we are responsible to provide the UK's physical flow and density measurement standards. And just to remark, we carry out a lot of research on behalf of the UK government on topics like metrology and flow metering. So, which are the sectors that we support? Historically, NEL worked a lot with the oil and gas industry, the water industry, and also mission monitoring. And now, the society as a whole is approaching new challenges, which are digitalization, clean fuels, decarbonization of our society, and also life science. And these are all areas that we are working on. We have teams on each of these areas that are conducting extremely nice research in these fast-moving and exciting and challenging areas. So just a quick overview of our facilities and our building. We have the James Young building, which has the gas facility. This is a dry gas facility. Mainly, we run it with nitrogen, but we also run it with argon, helium, and in the past, we ran it with the CO2. So we are planning to do that also for the future, for the topic of CCS. We have also our single-phase oil facility and our new hydrogen facility for domestic gas meter testing. Then in our new building, the Reynolds building, we have the new Advanced Multiphase Facility, which goes up to 140 bar gauge static pressure. And this is a fully multiphase facility where we can test flow metering, wet gas flow, as well as multiphase flow. We have our water facility and our EPAT, elevated pressure and temperature oil facility. Then the erosion facility and the primary density lab for fluids. Just a few words on our new facility on hydrogen. You can see the facility on a picture on the right-hand side. It's a very compact facility and was primarily designed to test the domestic gas meter, but we can test whichever meter you're interested in. It operates with hydrogen, nitrogen, and methane, a mixture of any two. So we can also test the performance of the meter with mixture of gases. This facility has been fully commissioned, and it operates with sonic nozzle reference meter laminar flow elements, but we're planning to build a primary standard for hydrogen for this facility. So that was a quick overview of NEL. Now we will crack on with the topic of the talk. So some wet gas application and terminology. Let's, for a second, assume that you have a nice glass pipeline, so a pipeline made of glass, so we can see through the pipe. And in your pipe, you have mainly gas, which is colored in green, and you have also a small amount of liquid, which is here in red. In this case, the gas flow on top of the liquid nicely, so it's called stratified flow. And this is the flow that we want to measure. Strictly speaking, this is a two-phase flow because we have the gas phase and the liquid phase. These are two phases. So our aim is to put here a meter and to get some flow measurement out of it, which are primarily the gas flow rate, because, as I was saying, the flow is primarily gas with a small amount of liquid, so that's probably our main interest. But most of the time, we are also interested in the liquid flow rate and the fraction of water in the liquid stream, because in the liquid stream, we can have different components according to our application. So let's see some of the application of wet gas meters. One of the first application, and probably where everything started in terms of research and development, was the steam generation. So the first correlation are for steam. What happens when you have a pipeline with steam? Well, if you have a drop in pressure and temperature, you can start to condensate some of the stream. So you will form some liquid water. And then the question is how your meter performs when you don't have 100% steam, but you have some amount of water. And that's when you need to use wet gas meters. And so that's for the power generation industry, but also it refers nowadays there are a lot of applications in the geothermal sector. So again, you can have some steam and some brine, and you have this two-phase flow that you want to measure for your process needs. Then probably one of the biggest application and a lot of attention and research was carried out for natural gas production / blue hydrogen production. Why I'm saying blue hydrogen production? Well, we are moving towards hydrogen and CCS and decarbonized society, but still probably natural gas production will still play a role in the near future, because we can produce what is called blue hydrogen by methane and methane reforming. Here you can see the picture, and I just put in the blue box what is an offshore natural gas production platform, for example. In these cases, most of the wells are generally wet. So what you get out of your reservoir is not just dry gas. You have a small amount of liquid as well. And the benefit to use a wet gas meter here are many. One of them is possibly to replace the Tesla separator, which is a bulky and expensive equipment. But you will have several advantages, which can be reservoir well management, production optimization, and flow assurance, and also digital transformation. This is also a key point, because a wet gas meter in your infrastructure will give you a lot of real-time data that you can use also for diagnostic or for example, for predictive maintenance. So that's a wealth of data you can get out of a meter. Just some word about which kind of fluids you will encounter during natural gas production. So again, you will have a gas, which is, of course, in this case, a natural gas, but you can have also some minor gaseous components. And you will have your liquid phase, which is most of the time is a mixture of condensed hydrocarbon and water. And the water in your liquid phase can be either condensed water, but also formation water from the reservoir. So this just to give you an idea of which kind of fluids you will encounter during natural gas production. Of course, as I was mentioning before, during steam generation, you have steam and it's all water, liquid or gases or gas water. Another application I want to mention is CCS, carbon capture and storage. Why? Well, we will need to transport CO2 either in gaseous phase or liquid phase, or also in what is called dense phase, so supercritical condition. And of course, we will all try to design the pipeline as such it runs with single phase flow. But if you have a quick look at the phase diagram of CO2, it might happen, it's not so unlikely, if you see the temperature and pressure ranges, that for some reason you can fall in the liquid gas region. So in that case, maybe you can have a flow of gas with a small amount of liquid CO2, that's a wet gas flow. Or, for example, you have a liquid flow and you start to, have some gas bubbles in your flow. So we need to pay attention there. Of course, we will try to stay well away from any phase change boundaries, but it's good probably to keep that in mind, and in case to have in the field some meter that can cope with wet gas flow. So there are some applications, and now I will go through some terminology. I will go through it quite quickly, but you can also see again these slides yourself with your own time, and there are a lot of info in the public domain. But how is defined wet gas flow? I was just generally saying a stream of gas with a small amount of liquid. Yes, but how do you quantify that? Well, generally nowadays we said that wet gas flow is a flow of gas and liquids where this parameter called local Martinelli, and here is indicated with the X symbol, is less or equal to 0.3. So when this parameter less or equal than 0.3, between 0 and 0.3, we said that your flow is wet gas flow. Alternatively, you can use the GVF, which is gas volume fraction. So when the gas volume fraction is greater or equal to 95%, roughly, we speak about wet gas flow. So briefly, what is the local Martinelli parameter? Really, really roughly speaking, to give you an idea, the local Martinelli parameter defines the wetness of the gas. So let's say X is 0, that means that you are in dry gas condition. You don't have any liquid. Okay. As soon as you start to increase X, the liquid loading, let's say, will start to increase. And if you go up to 0.3, which is the upper maximum level, that will be your maximum level of let's say, liquid that you can have to be defined wet gas flow. But you can go above, and that, if that's your condition, and generally that's referred more as multiphase flow. But there is a tendency also to, now to go a bit beyond the 0.3 at the minute. The gas volume fraction is a ratio of the gas volumetric flow rate and the total liquid and gas volumetric flow rate. So it's another way to define the wet gas flow. Other couple of terms, adimensional number, which are quite useful. We'll see this later when we speak about correlation and overreading. Crude gas number. This number is an adimensional number and define the inertia of the gas, okay, against the gravitational force. So again, roughly speaking, when you have high gas flow number, you have, the gas kinetic energy dominates. If you have a low one, the gravitational force dominates. Then another term is the density ratio, which is just the ratio of the gas density over the liquid density. The water to liquid ratio, water to liquid mass ratio, just represent the fraction of liquid in your, the fraction of water in your liquid streams. One is in terms of volumetric flow rate, the other in terms of mass flow rate. So you can go from mainly oil in your liquid stream, you are close to 0 water liquid ratio. Then if you go to 100 water liquid ratio, it means that all the liquid is water. So that was a bit of an overview of the terminology and application. We will move now to what are called flow patterns. And so I will show now to you a video to give you an idea of what flow patterns are. Okay. So hopefully you can see the video. It's a bit slow on my PC, but I think this is a nice video because you have some gas flowing on top of a liquid layer coming from the right on a horizontal pipe. And then we have a vertical section upward and a vertical section downward, right? And you can see here, this is not exactly wet gas flow. The liquid is a bit too much, but just to give an idea of what flow patterns are. So flow patterns, strictly speaking, is the distribution of the gas and the liquid, so the two phases inside the pipe. They can be distributed in different ways. For example, stratified flow, as I was saying before, the gas is on top of the liquid. But you see here that we have on the horizontal section, we have stratified flow, but as soon as we go vertical, we don't have any more depth. We have a liquid film around the wall and the gas inside. So a core of gas surrounded by a liquid film. So you can immediately see here that also the process conditions are the same and the flow rates are the same. The inclination, the orientation of the pipe will play a big role in determining the distribution of phases in your pipeline. And another video, again, flow from right to left. You can see a mixture of gas and liquid in a Venturi tube. And here what I want just to show is how also the geometry of your meter influence, the flow patterns. Because you can see here in the divergent test of the Venturi, a lot of, is going on. It's a quite chaotic flow there, and it's quite difficult to model, honestly. We can see here also what is called lag flow. You see, okay, the pipe gets almost all full of liquid at a certain point, and that's lag flow. So at a certain point, here we go. You have a pocket of liquid approaching. So you see, this is just to give an idea of the flow patterns. You can have different flow distributions like the pipe, and through experiment, we build during time what are called flow regime maps. And I'm showing two here as a function of the liquid and the gas flow numbers. On the left for horizontal orientation and on the right for vertical. So I also plot some diagonal line in red here, which show the Locke-Martinelli parameter X. So you can see we can have different distribution, okay? And what I want to go through with you briefly, because that's quite an important mechanism to understand how the meters work in wet gas flow. We can start, for example, here, the yellow dot, you have low flow number and low, both liquid and gas. So as the picture show here, we have stratified smooth flow, most probably. This is just an indication. We don't have to take this flow regime up too seriously, okay? That indication most of the time. So now we are going to increase the gas flow rate. The gas flow number. That means our gas kinetic energy is stronger now, right? What will happen is we will move in this direction. We are keeping the local Martinelli parameter at a constant value. And you see, since the gas dynamic force is higher, we will start to entrain some liquid in our in the gas phase in form of droplets. And the gas is strong enough to disturb the liquid interface, so you have waves and entrainment. Then again, we keep the local Martinelli constant and we increase the gas flow number, and this will increase again more the kinetic energy of the gas. And at this point, the gas is strong enough, let's say, to lift part of the liquid layer on top of the pipe or close to top of the pipe. You have to imagine that most of the liquid layer will still be on the bottom, but you start to form a liquid layer on the top as well. This is annular mist flow, and you have a lot of entrainment of liquid in your gas stream. And this is an important mechanism, okay? If we go then instead on vertical orientation, we start a high fluid and gas number, high gas and liquid flow number. And we are here in the annular mist flow, and we start to decrease the fluid gas number. And at a certain point, we will change flow regime, and we will go in what is called the intermittent flow regimes. Here, the gas force is not enough to balance the gravitational force, which is drawing down the liquid layer. This is upward oriented. So the liquid layer is going to collapse, and this will give intermittent flow. You don't want to work in this region, and because it's a quite chaotic region and it's difficult for the meter to perform correctly there. So that's just to say, let's be careful when we are in vertical orientation, because flow regime can really affect your meter. Nice things, when we go up to very high gas flow number, both the vertical and horizontal fixation start to behave similarly, okay, because you start to have close to the same flow regimes there. Gravity is not anymore relevant in both of the cases, let's say, or at least it's playing a lesser role. Flow regime maps, there are a lot of flow regime maps out there. A lot of research was spent there. Sometimes it really depends on the fluid properties, the pipe diameter, orientation. There's a bunch of things to care about. I just want to underline two of them. Most of the time, they're based on human interpretation. So someone that interprets the flow regimes inside the pipe. And sometimes they are based on low pressure experiments. So we need to be careful here. It's difficult to generalize these flow regime maps. What we are trying to do at NEL to fill some of the gaps, or at least to try to fill some of the gaps, we have invested in an X Ray device. So that's the X Ray. We have a big pipe that we can look through. So we have X-ray sources, and you see we can scan basically inside and look at a cross-section inside the pipe. And this is basically something that we can use at high pressure, because you cannot use a glass pipe or perspex pipe at 140 bar. So that will allow us to go at high pressure, and that's what we have done in the past, and we are doing. So we are developing flow regime maps at high pressure as well, a low and high pressure. Here you can see how the X-ray operates. That's the screen. And what we are doing, we are trying to develop this kind of flow regime maps according to the X Ray results, and using also machine learning algorithm, which are trying to reduce the impact of human judgment on these flow regimes. Also, we are using the response from pressure sensors installed. This all feed into the machine learning algorithm. So that was just a quick overview of flow patterns and some of the key mechanisms that much more about to say, but we will stop there. And we will move to wet gas metering with differential pressure meters. That's a lot of meters where you can use wet gas. I'm going to focus primarily on differential pressure meters. And I would say there are probably three main categories of wet gas meters. The first one would define that the single phase flow meter with correction factor. Okay, that's a single phase gas flow, and you just have one measurement. You don't measure the liquid amount or the water cut. Then you have the two-phase wet gas flow meters. Here you measure, you're trying to measure both the gas and the liquid flow rates, but you don't measure the water cut, so the fraction of liquid of water in your liquid. And the third category, let's say, is probably called, again, definitions sometimes are a bit gray, but I would say multi-phase wet gas flow. What I want to say is that in this case, you will meter the water, the hydrocarbon condensate, so you know the water cut here, you measure it, and also the gas flow rate. These are generally differential pressure meter with additional measurement devices. This talk will just focus on differential pressure meter of the first and the second category. So with and without pressure loss ratio method. And I'm going to discuss what is the pressure loss ratio method. So DP meters, we probably pretty know all about them. So they've been covered by ISO 5167. This ISO is currently under revision, so probably next year you will find an updated version of the ISO. Generally, the main DP meters are Venturi tube, Orifice, cone, and wedge meter. In single phase, as I was saying, they're covered by ISO 5167. In wet gas flow, we have two technical reports, ISO technical report, and which cover Venturi, Orifice, and cone. So you can go and have a look at them. That's a lot of information there. Very briefly, how differential pressure meter work. You have a flow to a restriction, and here you can think about the Bernoulli theorem. So you have a restriction, the flow needs to accelerate, and if it accelerates, the pressure at the throat, in this case at the restriction, needs to be lower. So we can measure the difference in pressure and relate it with the flow rates of gas. I'm talking about single phase flow. You will generally find a parameter which is called beta, and this is the ratio between the diameter of the restriction and the diameter of your pipe. So this is the equation that you use in single phase dry gas flow. And as a well-known equation, you find that in the standard. C is the discharge coefficient, which accounts for energy losses, for example, friction and other kind of energy losses. Expansibility factor, it accounts for the fact that gas is compressible. It's compressible, so we need to account for that when we have a difference in pressure. Then the gas density, that's an important parameter. We need to get the density accurately. And the differential pressure, that's something we measure. So what happens when you have wet gas flow? Well, we use, with differential pressure meter, we use the kind of similar formula that you have here, but we add this correction factor, this phi. And this correction factor in the yellow circle is generally called overreading factor. Why is it called overreading? Well, differential pressure meter, they have generally kind of a similar response to wet gas flow. And the liquid causes a higher measured differential pressure. So when you have a liquid in your gas stream, the differential pressure is higher than if you don't have the liquid. That's called overreading because you basically will measure, you will think that you have more gas than what is in reality. And this overreading is induced by the liquid flowing in your pipe. So we need to correct that. We need to account for this overreading effect in some way. And on the right, I just plot experimental chart for a Venturi tube, and you can see the overreading factor on the y-axis and the local Martinelli parameter on the x-axis for different line pressure, right? So in order to correct your meter, we need to get this correction overreading correction factor in some way. So the first thing, we need to have a function that describes the overreading, a relation. This relation can come from fitted correlation or experimental semi-empirical correlation or from modeling, physics-based models. But you need to have some kind of relation. And the overreading will be a function of some variables. And for simplicity here, I'm just showing the local Martinelli parameter and the density ratio, which is basically a function of mainly the gas, the line pressure. Second point, we need to know the input variables. So we need to know the function, but we also need the variables that goes in input to the function. And for example, here, let's say we have our function that comes from experimental results, like in this plot. We need to know first the local Martinelli parameter x. Second, we need to know the density ratio and select the correct curve. And then when we have done that, we will get our overreading factor, and we can fit that in our equation and correct the meter output. So this is a very simplified process, but it gives you an idea of what we are doing to get the overreading correction factor. One thing that I want to stress here, as this chart explained well, we need to know x, okay? So the overreading function is generally dependent on x, and x is dependent of the liquid flow rate. So we need to know the liquid loading in some way to apply any correction to DP meters. An example, let's start with Orifice meters, and in this case, I will just assume for a second that we know x. We have some second measurement that tell us the liquid flow rate, and we are able to fit this secondary measurement in our Orifice meter. But the Orifice meter itself just measures the primary differential pressure. Okay, so in this case, one of the first overreading correlation was developed by Murdoch, let's say, that's probably one of the first, if not the first. And that was, as I mentioned before, a research work with steam, wet steam. And as you can see, this is a function of the local Martinelli parameter only. Then for the development season 1977, you see we are going to introduce both the local Martinelli parameter plus another term which goes down basically to density ratio. And we have this n exponent here, which is 0.25 for chisel in this case. We go further to today, and we have a further correlation. And you see that the n parameter now is a function of the fluid gas number. Okay, and also of the water liquid mass ratio. So we have introduced further variable to our function, to our correlation. And of course, you can go into details of the correlation, in much detail later. You can ask me a question if you want. I'm happy to answer any question. But what I want just to give you the feeling is that correlations evolve. We have more parameters. And also, in this case, it's quite nice, this graph, because it shows you the importance of flow regimes. Because this n exponent with the correlation by Steven is related to the flow patterns. In this case, stratified flow is a bit of constant, and then you can see that it increase with the liquid entrainment process in our mist flow, and also is a function of the liquid properties. If you use Steven equation here, a population of orifice meters, you see if you don't correct the meter output, you have your percentage gas error on the y-axis as a function of the local Martinelli on the x-axis. If you don't correct that, is that the error is this diagonal line. You can go up to 40–45% error in gas flow measurement. Okay, that's something. But if you use the overreading correction factor, you are in the region ±2% of gas flow error. So that's pretty remarkable in my opinion. Again, this is a simplified case. This is not what you will find in the field. You need to know X. Okay. So one method to actually measure X at the orifice plate is to get a third pressure tap downstream. The flow here is from left to right. I didn't mention that before, but it's from left to right. So the pressure tap is downstream of the orifice meter. And we can measure with a second differential pressure transmitter what are called the pressure losses. And to calculate what are called the pressure loss ratio, which is basically the ratio between the pressure losses and the primary differential pressure. So one possible equation is this one, and you can plug in your PLR and get the local Martinelli. You need to know the dry pressure loss ratio. So it's important to predict accurately that as well. And this is just a case, experimental results we collected at NEL for a 8-inch orifice meter. And you see the error in gas mass flow rate, percentage error, as a function of X when using the PLR method. And you can see that you are in the region of ±5% error, up to close to 0.3 local Martinelli. That's again, I think it's quite remarkable. This method needs to be further developed, but there is there. It's a possibility, it's an option. Similarly to orifice meter, we can do the same with Venturi tubes. And again, we will start just assuming the simple case where X is known by some secondary measurement. I'm not going to speak about how you can measure that in this talk, with some secondary measurement. And again, another correlation that's specific to Venturi tube was developed by the Leo. And again, here I want to stress again that, there is a clear influence of the flow regimes in your meter response. Another correlation, which is included in ISOTR 11583, it includes also the liquid properties. And again, wanted just to show you the impact of correcting or no the output of your Venturi tube in wet gas flow. So again, the diagonal points are the uncorrected one. So you see, you can again go in the region of 40% error. But if you correct with the correlation I'm showing you on these slides, you can get around plus or minus 3%. Again, you need to know X in this case, so the local Martinelli. And that's just to show that this correlation can work also with different water-liquid ratio. So again, we can use the pressure loss ratio method similarly to Orifice Meter. There is an equation in RZTR 11583, which is in the public domain, and you can use that to get your local Martinelli parameter. The error here in gas flow rate, I think, is, if I remember correctly, is in the region of plus minus 6%. But there is a but. You can use actually this method. The equation in the standard in 11583 only at very low local Martinelli values. So there are limits there that we need to overcome in some way if we want to use this method in the field over an extended range. So that was an overview of the response of Orifice meters and Venturi meters in wet gas flow. I will move now to some R&D and give you some reference to some standards. So R&D that we are doing at NEL, in the past we have done a lot of research with Orifice Meter and Venturi tubes in wet gas flow. That research informed the development of ISO 11583, IJTR, the technical report. At the minute, what we are doing is research in vertical Venturi tubes. And also we are trying to, extend the limits of applicability of the actual overreading correlation and also of the PLR method, a higher local Martinelli value. That's of paramount importance if we want to develop this technology. As I was saying, establish foraging map with our X Ray device, also high pressure, and we have run a lot of experiments both in wet gas and in fully multiphase flow with the X Ray up to 130 bar, if I'm not wrong. So from 7 bar to 130. And here there is a list. Just want to say also that there is interest in CO2 wet gas stream, as I was saying, for CCS application. And also, I'm quite pleased to say that we are going to start soon a PhD project in collaboration with Sensis to develop a Venturi tube, a wet gas meter based on Venturi tubes. We are trying to redefine a bit the shape of the Venturi tube and also use some advanced diagnostic. And also here, the focus will be also to measure stuff like the liquid layer height, the droplet sizes, all that parameters that can inform some physics-based modeling. And that's quite important in my view because, if we want to progress in this area, I think an understanding of the physics inside your meter is of course, pretty relevant. And just to give you a feeling of some of the latest tests we've run, I think last week, a week and a half, in our Advanced Multiphase Facility. These were wet and multiphase tests. And you see it's a vertical Venturi on the first picture on the left. And this is, a design, you see, we have both straight tappings and inclined tappings. So the idea here is to use this Venturi tube both in horizontal orientation, so you use the straight tappings, and vertical orientation, we use the inclined tappings. And so far, we have found out, and also in previous experiment, we also wrote a paper at the North Sea Flow Measurement Workshop to show this, that the vertical tapping work well in vertical flow because one of the biggest concern is that you can float your impulse line with liquids, and when you go down the throat, it's not nice. I can tell you. So you definitely need to avoid to have liquid in your impulse line. That's also a lot of other solution. You can have your DP, you can reduce the length of your impulse line. You can have your DP kind of attached to your meters. So there are a bunch of different also methods, but this so far we found it was working okay. We were working pretty fine. We didn't have any accumulation so far, honestly speaking. And you see, the vertical Venturi is mounted on top of the X-ray machine. So we have the X-ray device after a blind T. So the flow comes horizontally, then you have a blind T, goes vertically, X-ray device, Venturi tube. And we collect a lot of data here, and the nice thing was we had the X-ray, so we could always get the information on the flow regimes. You know, we had this data set, we have previous data set, we were able to develop a new correlation for vertical Venturi. And, you know, we are planning to get the correlation out in some papers this year. It's a quite nice correlation so far. So, yeah, hopefully you will find that in some papers later on this year. Here are some standards and guidelines for your reference. Again, what I want to stress here is that there is a lot of information in the literature. You can see the proceedings of the North Sea Flow Measurement Workshop and the tons of papers about wet gas. You know, it's very nice to look at them, and there are a lot of details. And there are also as a standard, so that you can see here, just I put some for your references. And also, just want to say here that now you can find available ISO TS 21354 that was published, I think, end of last year, around December, if I'm not wrong. And this is TS on measurement of multiphase fluid flow. So again, there is a lot of info there. So this brings the webinar to the end. Just some key points. So we have covered some key definition and application. For example, natural gas / blue hydrogen production, and this is just me trying to stress the fact that you know, natural gas is going to play a role for blue hydrogen production. I hope I passed the message that flow regime is important, and so it's important to have an understanding of the flow regime in your pipe. A brief overview of Venturi tube's Orifice Meter in wet gas flow. We cover some of the key points, let's say. And what I want to say is that this kind of technology can be a robust, relatively cheap, kind of off the shelf. No black box, because as I was showing you before, most of the questions are publicly available. There are papers that are describing how the correlation and the physics-based model have been developed. So, you know, the user can understand by first hand what's going on in the meter. And as I was saying, there are no proprietary equations, so they are in ISO standard. R&D touched briefly some of area that we are working on, and please do not hesitate to contact us if you are interested to collaborate in this area. Also in the area of wet CO2, for example. And I've tried to give you some reference to international standard. And again, there are a lot of literature out there. So I just want to thank you, everybody, to listen to this webinar. I really hope you enjoy it. And I don't know if there were some questions, so I will pass to John.
Thanks for that, Gabriele. Well, yeah, we've actually had quite a lot of interaction during that presentation, so we've got quite a few questions. I'm not sure we'll get through them all, but we'll give it a go. The first one I've got here, and this is one that's close to my heart because it's certainly something that's confused me. Terminology. You talk about GVF as gas volume fractions. But I've also heard this term gas void fractions. Are they the same thing, and do they ever get confused?
Well, yes.
By me.
I think this is a pretty common question. Let's say. What I want to say here is there is a lot of terminology, and sometimes it's very confusing. During the years, people use, for example, the local Martinelli parameter itself, a different way to define it. And for example, as you say, the GVF. GVF can stand sometimes for gas volume fraction, gas void fraction. So it's easy to get confused. So it's always better to have a look at terminology, before doing some mistakes with calculation. But GVF in terms of gas volume fraction is different from the gas void fraction in general. They can be the same things under central condition, but they are two different things. Okay, so the gas volume fraction is the ratio between flow rates. So we are talking about in terms of dimension meter cube over a second. The gas void fraction generally is a ratio between cross-sectional area. So we are talking about meter squared. So if we want to pass from meter cube over second to meter square, there is a velocity multiplication there in some way. And that's what is called the slip ratio. So that's the difference between the two, is the slip ratio. Just to give a bit of a feeling, the gas void fraction is like if you look at your pipeline, you cut the cross-section of the pipeline at just one instant, you look through it, and you see, oh wow, half of the pipe is gas, half of the pipe is liquid. So your gas void fraction is 50%. So that's basically the portion occupied by the gas and the portion occupied by the liquid. But if you have no slip, so if the two phases are flowing at the same speed, that's also the gas void fraction. If not, then you need to calculate the slip and to multiply the void fraction by the slip to get the volume fraction. So it's like when you get a snapshot with a fast camera of two cars running in the street. And if you just take one snapshot, you will see the position of one car and the position of the other car, but you cannot determine the velocity. So that's basically what it is.
All right. Okay, thanks for that, Gabriele. Other question here, will the results of the R&D research that you showed in your presentation be made available at any point? Okay,
yes. What I was trying to say is we did a lot of tests also recently, and the answer is yes. We are planning to produce some papers at conferences or in a peer-reviewed journal, especially one that probably will be out there soon is about a correlation, a semi-empirical correlation that we developed for vertical Venturi. So yes, and again, if you want to collaborate, just let us know, and we are always happy to collaborate on this topic.
Okay. Here's a question here that I think I can answer. Someone's asking about testing large-scale meters in hydrogen. I think basically, yes, it is something we're considering. At this moment, we're focused on the small-scale hydrogen meters because basically that's where the industry is at the moment. That's as far as they've got. We know that there's plans to look at large-scale, but as part of our determination, we need to look at is a facility actually required, or can we use existing infrastructure, testing, for example, we tested nitrogen, so can we test in another gas? So at the moment, we're looking at it. We haven't made a determination. So the only thing I can say to you, if you've got a view on this, then that would help us make that determination, then we'd love to hear from you. So, get in touch with us, and that information will help us put forward a case for it.
If John, if I can just add a few words about that. Yes, we have a fantastic clean fuels team at NEL at the minute. We are not just developing the domestic gas facility. We have also some portable primary standard to test, a refueling station at the minute. And we are doing a lot of research and a lot of other projects. So, yes, if you're interested, please get in touch because there are a lot of more there that we are doing on the clean fuel side.
Good. All right. Okay. Here's one for you, Gabriele. Why is PVT software important when measuring wet gas flows?
Yes. That's a very nice question. I mean, of course, due to the time constraint, I couldn't touch all the aspects. But PVT software is one of the key aspects of wet gas metering, right? So you can have a fantastic meter, but if you don't have a good enough PVT software, you are a bit in trouble. This is something that is generally overlooked by some user. But it's of paramount importance because PVT software will kick in when you're going to calculate your fluid properties like gas density, liquid density. And so you need to have a good one. Also, I spoke about gas and liquid like different phases, right? This is not entirely true. In reality, you have some mass change between phases. So you can have, for example, gas that is going into the liquid and some liquid that is going into the gas. And if you don't account for that, and the only way is with a good characterization of your fluids and a good PVT software, then of course your measurement is going not to perform. So yes, PVT software are key. And if I can say a word there about also that we are working on that, and we have a software which is called PVT software, which is called PPDS. So again, if you're interested in that stuff, ring a bell, and we are happy to assist.
Good stuff. All right. Okay. We could probably go on for about another half hour here, but sadly, that's it. I'm afraid, folks, we've run out of time. As I mentioned earlier, we'll be sending a copy of the presentation and the recording out after this event, so you can recap on that. If you need more information, visit our website on www.tufsud.com. For more information, or contact myself and Gabriele. So on behalf of both of us, thanks for taking the time to join us today, and enjoy the rest of your day.
Yes, thank you. Thank you very much.